Okay, let me give you a brief uh, description of the stabilities of a cylindrical plasma column. Um, you can find the material in the Physics of Plasma, section 4.5.1. So on the chalkboard is basically anything on the right hand side is supplement derivation of the left hand side, and left hand side is the as a main structure flows of derivation. Uh, so we start from the second law of Newtonian mechanics, force equals acceleration, and the c is a displacement, or uh, basically the distance that they move. So we know that it can be if we take thinking about something, we think about the Fourier component of it, then um, we'll have I the d dt squared will become I negative omega squared. So we have F equals negative rho naught omega squared c. And we know the force can without we're talking about cylindrical column, so we don't consider the we're not considering the what's the name uh, the curvature. So we only have j cross b. We substitute j using the Maxwell's equation, and this goes to zero because we assume inside of the cylinder the pressure is homogeneous. And let's look at the first order. We will argue the first order P1 is zero as well. So let's look at the second moment. This is from the MHD equation, second moment, and then we multiply gamma minus 1 rho, and we just expand everything in terms of this. Basically, f and the derivative of that and derivative of that. We have those two components, and we're dealing with ideal MHD, so eta is zero. So we have this. Then we use the first zeroth moment. Substitute this term. This is d rho dt. Substitute this with this, and multiply 1 over rho. We're left with this expression. Of course, we do the derivative of those two components, derivative of that and derivative of that. So this term substitute to this term, and it become two terms right here. And we utilize the adiabatic law. Basically, p rho to the negative gamma is constant, and since it's constant, and then if we give it a divergence, give it a gradient, then it should give us zero, right? So this should be zero, and doing the gradient of this will equal to zero will give us this expression. Substitute this thing, you can see this to here, so gamma p grad rho, gamma p grad rho, so it will become u rho grad p divided by rho, then it will become u grad p. Since we're assuming the fluid is incompressible, then the grad u is zero, then this becomes zero. This becomes zero, and we know that if we take, so from here we take the first order, then u1 p naught p1, then it become this, and ddt is a negative I omega p1 plus u1 grad p naught. Grad p naught is zero since we assume it's homogeneous. Then we know that the negative I omega p1 is 0, then from this, since omega is finite, then we know that p1 is 0. So from this, put into here, to the first order, we know that the negative grad p is 0, based on the argument here. And this is 0 because this is the second order. So the j can be substituted to c over 4 pi c over 4 pi, and you divide it by c here, then the c cancels out. We have 1 over 4 pi curl b1 cross b naught. And we do the gradient on both sides. Then the right hand side becomes this. The left hand side utilize this identity. We can assume one of the vector, say this vector is a. Then we can write in terms of that. So b grad b1 minus grad b1 dot grad b. Grad b1 and grad b naught. Since we know that b naught is constant, then this becomes 0. So this expression become b naught dot curl b1. So a is curl b1. Oh, by the way, you know that the b1, the perturbation has a two component. One is theta and bz. From here, we can see this is 0 because we are assuming it's incompressible, and u, the velocity, can be expressed as dx psi over dt. So if this is 0, then this is 0 as well. Basically, this is the time integral of this. So this is 0 and this is 0 as well. So the right hand side is 0. So we're left with this whole thing equal to 0. And we utilize this vector identity. As you can, and from Maxwell's equation, this is 0. And we're left with this term. Then we have b naught Laplace b1. Laplace b1 equals 0. And since b naught is in the z direction, then we're only left with a b1z, bz, grad bz equal to 0. So then we can write bz in another form, and then this part, we need to use this part. So from induction equation, we have this, and utilize the definition of speed. Speed is the time derivative of distance. Then we have this. Basically, there's ddt here and there's ddt here. Then it cancels out. And we know that the grad is basically ik, and then this b1 can be expressed in this way. And we know that k is parallel to b naught parallel to z, b naught parallel to z, and we define c here, k is here. So we only do after we do the derivative, we'll only left with that term. So we have b1 equals ik b naught c. So substitute this to here. Since all the things here are constant, then we're left with Laplace z equal to 0. And we have the expression of definition have to see in this way, so that is periodic in terms of k and theta. This is a Laplacian for cylindrical coordinate. Then we're left with this expression. This expression is the standard format of a modified Bessel functions. There's two modified Bessel functions, one of which will be finite at r equal to 0. So which is I. Since we cannot, we want convergence with inside of the cylinder, then we left with this expression for the given boundary conditions. This is already applied the boundary conditions, and we can write c r and c theta in this way, and we can utilize this part to showcase why is that. So let's start with from here. So this is this, but just apply B1, plot B1 to here. We'll have this. See, we just B1 become cos C, become IK B naught cos C. So and the B naught become B naught Z. So B, then we have K B square here, and I divided by -1 divided by I here, and then that's the same expression as this. So we do the curl. If you check the books, the handbooks, you will see the curl in the cylindrical coordinate is such. You can write in this way, and you can do the derivative based on the definition of cos C. So we have this. So that's R component of this, and cross C, the component cross C, and this, and it should, so different components should match with a different direction should match with different direction. So this one will match with that one. This one will match with that one. So we'll end up having two equations from here. If you tidy it up a little bit, you will find out those two equations will result into those two expressions, and this give us a complete descriptions of a perturbed field inside of the cylinder. So from here, you can using this to express B1, as you can see. So all of the things are given for the given boundary conditions. That's inside, from here to here is the inside of the cylinder. So let's consider outside of the cylinder. We can write B1, the perturbed magnetic field, in terms of this way. We know from Maxwell's equation this is true. So plug this into here, then we have the Laplace phi equal to 0, and this is the same. This is the same structure of this expression. So we will have the same answer, which is modified Bessel function. Since it's outside, we want it to converge. We want it to be 0 at infinity. So this is another type of modified Bessel function, which is k. So we're left with this expression to describing the field outside of the cylinder. So this is the field inside of the cylinder, field outside of the cylinder. So if we so there's, of course, at r equals a, then those two are connected. So we need to make sure those two expressions will meet a certain boundary conditions, and those are three boundary conditions. Those two comes from the Maxwell's equation. this comes from basically the pressure balance, force balance, or rather pressure balance or force balance from this. And after a lot of math, you will end up having this dispersion relations. And this dispersion relations can give us some information of stabilities. Since if the right hand side becomes 0, then then omega will be an imaginary number. Thus, we will have instabilities. Of course, I will derive this in further detail for next videos.